Titration is the final of the three methods for making salts. We use it when we have a soluble base. If you remember the last video where I dealt with general method, we used general method when we had an insoluble base reacting with an acid. Well, here it's when we've got a soluble base reacting with an acid. Now, soluble bases are called alkalis. So alkali, acid and alkali, general equation you should know, make salt and water. Now, if I demonstrate this with the particular making of the salt called sodium chloride, then we can discuss all of the issues that arise with this method. And let's have a look. Well, this is a reaction. To make sodium chloride, you'd need to react the acid, hydrochloric acid. So from the hydrochloric acid, you get the chloride bit. And from the soluble base, sodium hydroxide, you get the sodium bit, sodium chloride. So sodium chloride and water are the products. But do you remember the general method was one where we started with an acid and we added more and more base. And then we added more base and more until we had excess base. Well, how did we know? How did we know we had excess base in the previous video? It was because the base was insoluble. The base kind of hung around. It was either sank to the bottom or floated around, and we knew we had excess because we could see it with our eyes. That's the problem. With a soluble base like sodium hydroxide, it won't hang around. It will dissolve in the water. You won't be able to see it, and therefore you can't just keep adding more and more and more and more until you can see it in excess. That won't work. The method fails. So that's what this bit says. How would you know? Well, you wouldn't know if the base was soluble when you had excess. I can demonstrate that, but we need a totally different method, and that method is titration. We'll explain in a minute. But before I get on to the titration method itself, let me deal with this aspect of this reaction, the acid and the soluble base, sodium hydroxide, reacting together. Let me show you. So here I've got some hydrochloric acid. I'm going to put hydrochloric acid into this beaker. So that I can use it more easily. And I've got the soluble base, sodium hydroxide, and I'm going to put that into this beaker. Now, I've got an empty beaker here. I'm going to move that back so you can see it. So, empty beaker, this is where I'm going to carry out the reaction. So let's start with some acid. Do a glug of acid. There, we've got some acid. And we need to react with base to make salt and water. The base, soluble base sodium hydroxide. There. See that reaction? Not a great deal to see, but you know there's a reaction. You know the acid, hydrochloric acid, is reacting with the base sodium hydroxide. But you can't see the reaction. You can't follow the reaction. You can't put more of this in. Well, you can put more of this in. You put more and more in. But how do you know when this base is in excess? Now, some of you might think, what a twazzock. Why doesn't he use an indicator? There you go, indicator. The indicator, I like this indicator called phenolphthalein indicator, and I'm going to add a couple of drops. Now, this indicator, if I have a couple of drops, that will tell me what is present in excess, whether it's the acid or the alkali. Now, to remind you of the colours, alkali, Phenolphthalein is red. And colourless if it's not alkali. So let's put 2 drops in and see. 1, 2. Ah. Now you know that excess is acid. Well, let's put more alkali in. Ah. We have excess acid. More alkali. We have excess acid. More alkali. Now we've got excess alkali. We don't want excess alkali. We don't want the excess alkali to mess up our crystals. We don't want the excess alkali to be an impurity. And therefore I want to react it away. And I'll react it away with acid. This is the acid. Oh. Now I've got excess acid. That excess acid now will mess up our crystals. It'll be an impurity. Not only that, I've got indicator in there messing up our crystals of sodium chloride. If we want pure, dry, nice, big crystals of sodium chloride, this method's rubbish, because either we'll know we've got excess acid or we know we've got excess alkali. So is there a point at which we can get just the right amounts of acid and alkali? Well, you might have to use drops rather than glugs like I did. So if I just put drops of this in there, drops of the acid, and stir it after every drop, or swirl it is the better word, swirl it, now I've got extra acid. Now it should be possible to get to a point at which one drop accuracy will give us the colour change we want from colourless to red. So we're approaching it. Now one drop. That reacts away. One drop. Can you see it takes longer for that pink or red coloration to react away each time? Because we're approaching the point at which the acid and alkali are just balanced. One drop. That pink tinge is not going. That pink tinge, you might not be able to see it in the video, but I can see it here. It's a slight pink tinge. I'm just going to make it more obvious by putting one more drop in. There, one drop. See that pink tinge now? That's about as good as we can get using this apparatus. We can get more or less the acid and alkali balanced, but there's a problem, isn't there? The problem is, if we make crystals from this, sodium chloride's been made, there'll be water in there, but we've got indicator in there. And the phenolphthalein indicator, or any other indicator if you want to use other indicators, will be an impurity and it will mess up our crystals. And therefore, that's the theory I want you to understand. That's the idea behind what I'm going to do. But we have to do it in a much more accurate, much more methodic way where we don't need to use indicator. And that is why we need to use a process called titration. It's very precise. And when we know precisely the volume of acid and the volume of sodium hydroxide. When we know those precise volumes, then we can do the mixing of them and the reacting of them without using any indicator. And that's what I'm going to show you with the method of titration. And it's this method of titration you want to know, not this demonstration that I've done here. That's for understanding. I'm going to show you the titration next. Let me put my video on pause. Okay, so I've got some apparatus here to show you, which is the apparatus you need to do titrations. So we've got indicator, that's the same indicator I used earlier, phenolphthalein. We've got a conical flask in which we're going to do the reaction. Conical flasks are good because when you do the swirling, you don't slosh the chemicals out. They might slosh against the sides here, but rarely do they ever slosh out. So you need a conical flask to do the reaction. This thing here, this thing is called a perpet. And if you read it carefully, the text on it there says it measures 25 centimetre cubes at 25 degrees Celsius. So this room, warm day today, is about 25 degrees Celsius. And at 25 degrees Celsius, this will measure 25 centimetre cubes accurately. It'll measure it accurately to 1 drop accuracy. And you see that mark there where my finger is? There's a mark there which, when I fill it to that mark exactly, then it's exactly 25 centimetres cubed at this kind of temperature, accurate to 1 drop. So, very exact piece of volume measuring apparatus called a perpet. Now, don't mix the two things up. Perpet and burette. Perpet, it looks a bit like a snake charmer kind of instrument. Maybe that is a bit daft if you don't know what a snake charmer instrument is. Anyway, the other piece of equipment I need you to understand is this piece of equipment here. Now, this is a really long tube, and this is a burette. Now, if you look on the burette, there are markings, start at the top at 0, and they come down all the way to 50. And each of the small divisions is a tenth of a centimetre cubed. Again, very, very accurate piece of equipment. And when the tap is that way, that's closed. When it's with the burette like that, that's open. So open, closed, open, closed, etc. is how we use it. Now I'm going to mount it. I'm going to mount this. I'm going to mount it on a stand here. Mount it on the stand. And I'm going to put the conical flask underneath. And this is a small funnel, plastic funnel, with which we're going to fill the burette. Now you need to make sure that the tap here is closed. Close the tap. You need to get a beaker, that's a scrap beaker, just to take the waste. Put that underneath first. Then you get the small funnel. You put it in. And I'm just going to take you to the top so you can see what I'm doing. Small funnel at the top. And I'm going to fill that with alkali. I'm going to fill it with sodium hydroxide. exactly the same sodium hydroxide that I had before. And that's why you have to make sure your tap is closed. Otherwise, while you're doing this, if your tap's open, you're looking at the top and the tap will be leaking at the bottom. And you fill it up so that it's close to the top. It does not have to be at zero. Indeed, you just waste time trying to get it to zero. You don't get it to zero. You see? I have got it, where is it? I have got it to, where's the zero? Here. Nearly zero. And then I'm going to just divert your attention to the bottom. I'm sorry, my phone can't take the top and the bottom. So now when we're at the bottom, we need to open the tap to run some of this into your waste beaker. Now there's air here. The important thing is to make sure that air gets expelled with the pressure of the alkali above pushing it out. So you open the tap there, and you make sure that any air bubbles have left. So no air bubbles in there. Indeed, you know it's alkali because that's the same beaker I had before. Loads of alkali. That beaker's gone much more red now than it was before. So the burette is filled with alkali, and you need to take an exact reading. Now an exact reading, let me try and show you. You need to take an exact reading. The exact reading has to be at eye level. I don't know if you see that. That reading, I can't seem to show it to you very well, but that reading is at eye level 3.8. 3.8 centimeters cubed. So if I write that down on the board, initial reading was 3.80 centimeters cubed. Now you need to write stuff like that down, otherwise you'll forget it. So 3.80 centimeters cubed is where we're starting. That is our starting point. And what we need to do is, in this, we need to put our acid. And we're going to put exactly 25 centimeter cubes of acid using the perpet. So if I divert your attention down here, divert your attention here, this is the beaker of acid I started with. Maybe if I take it back you can see more. More about what I'm doing. Okay, so perpet. In the old days, we would put this and we would suck. And that's why I remember it being like a snake charming device. We would suck up using our mouths. We would suck up the, the acid. We would suck up the acid with our mouths. But then sometimes, if you inadvertently lifted the perpet out of the acid, then it shot into your mouth. You got a mouthful of acid, which wasn't pleasant. Nowadays, with health and safety, we never suck. So we use these kind of devices. Perpet fillers. There are now various perpet fillers, but these are the ones that my school uses. They're called pipe pumps. And what you do is, it's like a big syringe. If I do that, it sucks up. I'm sucking up. And then if I keep sucking, keep sucking, and I take it way past the mark. Now, can you see? I've got my finger over the top, I've taken out the pipette filler, and I don't know if I can show you, you can see the mark there. Now, if I release the pressure, then it goes down and down and down until the bottom of the meniscus sits on the mark, on that line there. Now, it's on the line. That is 25 exactly. I get that. And I'm going to release the pressure off my finger, and that will then run out. You can see it running out into the conical flask. And that's me delivering exactly 25 centimetres cubed of acid to an accuracy of 1 drop. Now let me show you this end bit. That end bit looks as though it's got some acid trapped. You do not blow it out. You leave it. Indeed, you have to leave it. If you knock it out or you blow it out, I've blown it out, there's nothing there, then you've delivered more than 25. To deliver 25 exactly, you can remedy the situation by putting this back in and touching. If you touch it, then it sucks back the exact amount. You need to have a little bit of acid left in there for you to deliver 25 centimetre cubes exactly. Now, that's 25 centimetre cubes exactly of the acid, and then I need indicator. So, indicator 2 drops. Indicator 2 drops. That is ready for my titration. I'm going to move that beaker away, because that was a scrap beaker, and now I'm going to put the conical flask there, and I'm ready to do the titration. Now, I hope you can see clearly what I'm going to do. I'm going to run there, I've opened the tap. I am now running, the alkali, I'm running it into the conical flask. Turn it off. That's off. Can you see? If I swirl it, all the alkalis reacted. So I've got excess acid. And I'm going to just carefully add a bit more. I'm getting close now. I know as an experienced teacher that when it takes longer for the pink coloration to go, then you're getting closer and closer to having the same quantity of acid as you've got alkali. I'm just putting a little bit in at a time, little bit in at a time, little bit in at a time, and I'm swirling it to react it away, and it's reacting away, little bit more, and more, and more, and now it's taking a bit longer. So I'm adding less drops each time. Now, I'm almost there, I can feel it, but you can, I hope you can see this, you can organise this so that it drops in 1 drop at a time, slowly, like that, drop, swirl. Then, he says, next drop there, swirl. Now that's 1 drop accuracy. You could just have it set to be delivering 1 drop very slowly and do 1 drop at a time until you get that permanent pink coloration. I'm going to speed it along a bit more, a little bit faster than that. just because I don't want the video to be too long there, 1 drop's gone in, swirl it. 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 1 drop's going in, swirl it. 1 drop's gone in, swirl it. Whoa. 1 drop's gone in, swirl it. And there, the colour's now not changing. There. The colour has gone permanent red. I've turned the tap off. That there, within a few drops accuracy, is the exact quantity of the acid reacting with the alkali. So the acid has reacted with the alkali, and there's a tiny bit, 1 drop more alkali. So almost the acid and alkali have reacted such that there is no excess acid and no excess alkali if you ignore that 1 drop. But the problem, of course, is that we've got indicator contaminating it. Now, if I just get the volume reading now, volume reading here, you see that top there? We need to take that exact reading. So I can't hold the phone and do that, so I'm just going to do it. I'm looking at it now. It is 29.05. Final reading, 29 point, sorry, I forgot what I said. Was it 0.5? 29.05. 0.5 centimeters cubed. Okay. So let me have a look at this. If the final reading was 29.05, the initial reading was 3.80, then the titer value, that's how much you used from the burette into the reacting conical flask quantity. That titer value will be, well, you subtract these two. So 5 take away 0.5, 2, 5, 2, 25.25 centimeters cubed. So now you know that within a few drops accuracy, 25 of the alkali is needed with 25 of the acid. Now the first of these is always a rough experiment, like I've done there. But then you repeat it. You repeat it over and over and over and over again. You do many repetitions. Maybe you'll need, most people will have to do about 4 or 5 repetitions. If you start with 25 of the acid each time and look to see how much alkali is needed each time, if you get values that are within 0.2, so concordancy is within 0.2 centimeters cubed. Well, what that means is if you do the practical over and over again, the values that are within 0.2 of each other will be the reliable ones. All other values you don't use. So say you do it 5 times and you get 20, 25, 25, 30 and 15 and 25. Well, you would ignore those. You would ignore the 30. What I'm trying to say to you is, if you've got a bunch of readings that are the same experiment, if you keep doing it long enough, you'll know that the answer is round about this value, which in this case is 25. If you get values that deviate, you know that they're likely to be full of errors, and error experiments, we can talk about them being anomalous, we can ignore. So ignore those and use the ones that are concordant, use the ones that are within 0.2 centimetre cubes of each other. And when you've got, say, 2 or 3 or 4 concordant results within 0.2 centimetre cubes of each other, then you take an average. Having got your average, the average titer value, that's what all this titration is about, working out the average titer value. When you get your average, having got the average, you then do the experiment once with no indicator. That means we're going to put 25 centimetre cubes of acid, and we're going to put the average value we get of alkali together, and we're going to put them in an evaporating basin, and then we'll know with those quantities we can be sure that the acid and alkali will not be in excess, and there's no indicator. That will ensure at that point we only have salt and water, and when we've got just salt and water, then we can boil it. We can boil away the water, concentrate the salt, we can leave it for days for nice crystals to form, and after days come back, we can filter off the crystals and we can dry the crystals in a desiccator. Now all of that we've done previously. So the different thing here is the titration, the demonstration that I've done. Now let's get back to my PowerPoint. And take you through all of that with my PowerPoint in a more sensible way. My pointer's not working. Here. So, new method titration. This is the apparatus. So please learn burette, conical flask. Actually, you need a perpet. This thing here is a perpet. You need that there. You need to know about this perpet. I hadn't realised it wasn't there. So a perpet with a perpet filler, perpet with perpet filler, that delivers for you an exact quantity of acid in there. And then you use the burette to do the titration, you get an exact quantity of alkali in the burette. And you do it over and over and over and over again until you get the average. Having got the average, then you do it once with no indicator, and then you put that in here. You boil it to concentrate the salt. You leave it for days. See there? You leave it for days for crystals to form, and after days you come back, you refilter, etc. So that's the apparatus. It's not the full apparatus. I thought it was. I'm sorry about that. But you need to know about the burette and the perpet. And there's no perpet on that slide. Perhaps I need to change that slide. But this is a big method to write. In an exam, if you write it, you need all of those steps. And there will be about 12 allocated marks for that whole method. Let's see where the marks would be. With any salt, you're going to have to pick the correct acid. And I would put that acid with a perpet. I'd put it into a conical flask. That's where you'd start. Then you want the alkali to react with it, just like I did here, acid alkali. The correct alkali to react with it, and put that in a burette. Now, those first two steps, It's probably about 4 marks for those. 2 for the right acid alkali and 2 for one putting it in a perpet and one putting it in a burette, or using a perpet, using a burette. Then the 5th mark, or the 3rd step, would be add phenolphthalein indicator, which is the one I like, the colourless and the red colours indicator. I like that one, but you need to know methyl orange as well, and whether you got methyl orange or phenolphthalein, the colours will be different, that's all. But put an indicator in, and you know what colour it will go with the acid in the conical flask. Then you run the alkali into the acid, until the indicator changes colour, which with phenolphthalein will be red. It'll go from colourless to red, as I showed you in alkaline conditions. And then this step 5, repeat. Repeat over and 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 over again until you get concordant results. And by concordant results, I mean the titer values must start to agree to within 0.2 centimetres cubed of each other. And the ones that do, those, not any others, the ones that do agree, you work out the average concordant titer value by adding them up and dividing by the number of titrations. So say you've got 4 values that agree to within 0.2, then you divide by 4, etc. I hope you know how to work out averages, so I'm not going to get into that. I'm no maths teacher. Step 6. Now you repeat the experiment. Last time you repeat the experiment, now you use 25 of acid using your pipette, and you use the average value calculated, the V. You use the average value of alkali with no indicator, and you put those volumes in some apparatus, beaker, evaporating basin, conical flask, doesn't matter. You repeat with no indicator, with those values. And that will leave just a salt solution, and now you boil. You boil that solution until the crystals start to form, and then you leave it for days. After days, you come back, you filter again, and you dry the crystals in a desiccator. You see, that's a pretty long, involved method. Now, when I teach this, I spend a period talking through all of these ideas, and then the pupils spend a double period doing this. And in a double period, then they get about 4 or 5 repetitions done. And out of 4 or 5, normally you discard the first one, because that's the first time you know roughly how much it's going to take. Then the second one, you can be very careful and do drop-wise addition around the value that you got first time. So you hone in on the tighter value, and having honed in on it, then the ones after that, once you've done 1 or 2 initially, then you start getting the concordant results after that, and they might have 3 results after that that are concordant, or they might do 4 experiments after that and find 3 of them are concordant and 1 of them they can ignore because it falls outside the range of concordancy, and the range being 0.2 centimeters cubed. So with real results, you have to decide which ones you're going to use and which ones you're going to discard, and then use them to work out the average. And the average is V, that V there. When you've got that V average, then you know to do the final experiment with that volume with no indicator. And then that final experiment where the salt solution is put in an evaporating basin or a beaker or a conical flask, you know there's no indicator, and you know that's just the right quantity of acid and alkali. The acid and alkali are exactly balanced within a 1 drop accuracy to give you the salt, and therefore there won't be the impure indicator or the impure excess acid or impure excess alkali contaminating your crystals. Your crystals will be pretty pure, and you filter after days when you've got nice big crystals, and you dry them in a desiccator, and that's how you make these salts by titration method. And that is the last of our methods. Now, I've been working with this, which I grabbed off the internet, as a way of what method do you use to do various methods. Now, we've learned 3 methods of making salts: precipitation, general method, and titration. When do we use them? Well, I'm going to simplify that into my own flow diagram. My own flow diagram, well, can we come back to that? But my own flow diagram summary, I want you to learn this. There are 5 methods of what it is we're reacting, like excess insoluble metal with an acid. So basically, A is metal with acid, B is base with acid, C is carbonate with acid, D is titration, E is precipitation. Now look, those first 3 is the general method. Now, if you don't know what I mean by the general method, my previous video goes through it. That's the most common method. There's about 8 marking points with that one. Then today, we've done this titration of acid with an alkali to make a soluble salt. Titration method. That's what I've done today. That's the titration method. And there's about 12 marking points on an exam for that. 2 videos ago, precipitation method I did. And there's about 5 marking points for that. So there are 3 methods. Learn that there are 3 methods. That's when you use them. And the flow diagram I want you to know is this one. Is the salt soluble? If it's not soluble, then there's only one way to make it. You make it by precipitation. There. Is a salt soluble? Yes. If it's soluble, ask yourself, does the name begin with sodium, potassium, or ammonium? If the name begins with sodium, potassium, or ammonium, then use titration. Then use today's titration. If it's not sodium, potassium, ammonium, say it's copper sulfate like my last video, then use the general method. And the general method is react an acid with a metal. If it's reactive enough, react an acid with a metal oxide, react an acid with a metal hydroxide, or react an acid with a metal carbonate. 8 marks. So that's the biggest method. That is the most common method. That is the shortest method. This flow diagram, the flow diagram, I think, summarizes the topic. And my boys, sorry, I teach in a boys' school, but my pupils, they have an issue. They don't know when to use what method. Learn that flow diagram. If you learn the flow diagram, then you will know when to use what method. Okay, I'm going to just stop there.